Welcome to the MOOC course on disease clusters. This is a very important aspect for public health, and it's one that is very important to a number of communities, and an area in which communities can actually make a major contribution to our understanding of exposures and disease. I'm starting with some definitions of these terms so that they'll be familiar to you, and also you'll understand when you hear them in a discussion of environmental health. So what is disease, and what is a disease cluster? What is a disease cluster? A cluster is really fairly simple. It means something that happens that isn't random. And that could be that it happens during a specific limited time point, as shown on the left-hand side of this slide, which is looking at cases of an infectious disease in Brazil. And you can see in this slide that they are really clustered at the right-hand side of this slide, indicating something unusual. On the right-hand side, we have a clusters of space. And the different colors on this map, which is of the city of Baltimore, indicate where lead exposures are highest and most prevalent. And this goes by increasing intensity of this orangey red color. And you can see that there are areas that are completely blank, in which there were no children found with lead exposure. And then you can see that the distribution of children with higher levels of lead is not random and appears to have a pattern of cluster. And the clustering suggests to us that something unusual is happening. Because, of course, people are getting sick all the time. People may be exposed to lead all the time. And if there's no particular pattern, it's very difficult even to start looking for a specific cause. What is disease? Disease is the formal definition from the World Health Organization and others, is a manifestation of a specific change in health. And I want to stress those words because it's very important that we define what a disease is once again so we can investigate potential causes. And we think of a disease as something that impairs our function or our ability to survive, because it may even result in premature death. So how do we define diseases specifically? First off, as shown in the top bullets, diseases are often defined by the organ systems that are affected, such as the heart, the brain, liver, or lungs, or even more specifically, for example, in the case of cancer, we talk about lung cancer, breast cancer, prostate cancer. And these distinctions are extremely important because oftentimes they point to different exposures or causes. Now, diseases may be even more specifically defined within these categories that I mentioned above. So, for example, in cardiovascular disease, diseases of the heart and the circulation, we often talk about hypertension or high blood pressure, coronary artery disease, which are effects on the blood vessels that actually support the heart, atherosclerosis, which are effects on the rest of the circulatory system, infarction, or stroke, sudden diseases. Oftentimes, diseases have been named after the first person who diagnosed the disease, which seems a little unfair. Maybe it should be the first person who had the disease, such as Parkinsonism or Huntington's chorea. But the specificity is extremely important for the detective work that we all want to be able to undertake. So let's start out. There's reason that you have, or a health department has, or I have in doing research, that there may be a cluster. That is something other than just a random series of events that occur in terms of time or space. What is the health problem? And now you see the importance of defining a disease. Who are the cases? These are the people who have the disease. Where are they? Where did they live? Where did they work? Or what other geography might describe them more precisely? When did they get sick? Or when did they die? And so you see the where and the when become very important for our detective work. We can be even more detailed in terms of types of disease. There are infectious diseases. There are diseases like stroke that are acute, happen very quickly. Many diseases, however, are chronic, like cardiovascular disease. And these are the most challenging for us to study. And we want to really bore down on this question of the type of disease because the more specific we can be, the better it is for detective work. Many diseases are common. This is why we have to be specific. I'm going to talk about sentinel illnesses later, but it's part of this story. And many diseases actually include several specific diseases, for example, cancer. And I'll show you some data which indicates why it's important to look at specific cancers rather than all cancers in terms of refining our ability to do detective work on the cause. So, let's focus on cancer because this is a concern of many investigations of clusters and certainly of many communities where there's reason to believe that there may have been exposures to chemicals that we know to be associated with cancer. Cancer is one of those big baskets that contains a large number of related diseases. What I'm showing you here is a drawing based on an electron micrograph of what all cancers have in common. This is a cell that's dividing. And on its outside, it's got specific markers that indicate that it's a cancer cell, and it's going to be very resistant to most kinds of treatment that we can deploy to prevent or treat disease. The reason I'm showing a dividing cell is that in all types of cancers, cells begin to divide without stopping. So it's uncontrolled cell division and growth, which spreads into surrounding tissues. These extra cells can eventually form what we call tumors. And these may be hard, that is, within tissues, or they may be circulatory, such as lymphocytes. But all cancerous tumors are malignant in that they're really taking the place of healthy cells within an organ or a system, and they can also invade nearby tissues. We call that metastasis. So we know that sometimes liver tumors can metastasize to the lung, which means that they're actually spreading from one organ to the other. Cancer usually develops through stages, and a variety of different changes that involve genetic change going from the normal cell type on the left, and let's call this skin because it looks a little bit like skin, with the epidermis on the top and the dermis down below. And as these cells start to change, they first start to divide out of control, hyperplasia, that means dividing without control, and then they actually begin to change. So you notice going from the second picture to the third, these cells look different. And at a certain point, they have now replaced all the normal cells within that tissue. And that is why, for example, for skin cancer, it is a very dangerous condition. Now, these stages respond to different types of risks. So cancer is a multi-stage process, and there are different types of risks that govern each one of these stages. The first stages are really related to a genetic change, and this might be inherited, like the breast cancer gene, or it could result from damage, exposure to a carcinogen, such as through smoking. The next stage is when these cells start to spread, and this is often driven by chronic inflammation, in fact, by the coincidence of an infectious disease. And this is why we see interactions between chemicals and hepatitis, for example, in liver cancer. And these infections themselves can drive cancers. We know this from study of AIDS and, again, hepatitis. Also, endogenous agents, chemicals that are normally part of our own system, such as hormones, can cause cancers to spread and to continue to multiply. In this talk, I'm going to spend most time talking about chemical exposures because these are really the set of cancer risks that we have the greatest opportunity to prevent. And that's why there's so much concern and interest in public health and medicine in identifying these chemicals and then trying to prevent human exposure to them. So If we think about chemicals as preventable causes of cancer, and I can include smoking here as well, of course, because this is something we can stop, rather than the other kinds of things like genes or endogenous chemicals, they're very widespread in our environment. This is a map over on the left-hand side developed by the U.S. Environmental Protection Agency, and it shows a listing of all those places in the United States where toxic chemicals, including chemicals that can cause cancer, have been dumped. And you may have heard of the Superfund program, which was a government program to identify and clean up these sites, and whenever possible, get the industries responsible for dumping these chemicals to pay for this cleanup. But in any event, there are almost 2,000 of these that have been identified over time. And the ones in red are sites that are not completely cleaned up. And the very few little green ones are the ones that have been totally cleaned up, and the yellow ones are the ones that are in progress. So we've got a lot of places all over this country. But you can also see that there are real clusters of these places. These are not evenly distributed throughout the United States. So this is a source cluster. And it's not surprising if you have clusters of sources, you're going to have clusters of disease. Cancer is very common, and therefore it raises all these challenges that we have to be specific, to get as much information that we can to build our case for detection of the cause as well as the outcomes. Because every year, nearly 2 million people come down with cancer, and over 500,000 people die in the United States. This is not a rare disease, although certain cancers are rarer than others. And these are more data and statistics, and you can get all this information from the National Institutes of Health, and I've given some websites on some of these slides where you can get further information about how many new cases occur in women and in men, and they're different. Now, this is why we have to be specific. This is a graph done by the National Cancer Institute of the National Institutes of Health, looking at all cancer incidents in the United States from 1975 to 2015. And it goes between about 400 and 500 cases per 100,000, or 4 to 5%. There's not a whole lot of change here, is there? And it doesn't look as though we're seeing much of a cluster over time, because we're going from 1975 to 2015. So it looks like it maybe went up for a period of time. It was probably when we were still smoking a great deal more than we are now, and then it kind of flattened out. But it doesn't give us any sense of clusters occurring over time, does it? Now, let's define this a little more closely. Let's take one cancer. In this case, we're looking at a lymphoma, one of the most common ones, non-Hodgkin's lymphoma. And here, we can start to see real time-related differences because we're asking a much more specific question. Same time period, same collection of data, but looking at just one specific cancer. So as good detectives, we've got to be as specific as we can when we're looking at a cluster.